So today we calculate this DTL fan out. Last time we just stopped here, right? So you already mentioned that how to calculate the fan out, fan in. So high state fan out and high state, low state fan out, right? But the high state fan out means IOH by IH and low state fan out means IOL by IIL. So that means how many, this single gate, how many gate it can drive at the load, or how many load it can connect it with this single output. So today we will talk about, this is the DTL circuit. I hope you can understand. This is the DTL NAND family. So we already show it two input NAND gate by the DTL diode transistor. So DTL diode transistor logic. So we have diode, we have transistor. This is known as DTL circuit. Of course, we should have some resistor. These are the biasing resistor for the transistors. Okay. So now what we have to do, we have to connect some output here. For example, we have to connect just another input here. Similarly, right? Just I try to draw another DTL here. So this is my one DTL logic circuit. Now we are taking output here, VO output here. Then we connect one DTL. So it can connect number of DTL circuit here. So we have to calculate this DTL fan out. And some parameters are given. For example, the resistance value is given, VCC is given. The beta value, transistor beta value is given. Beta value is 20 is given. Okay. Now we have to calculate this fan out. To calculate this fan out, we have to calculate those, apply some KVL and KCL. So that means if we think that we have the output, low output here, IOL, that means it's sync, right? When the output is low, output current is low, that means it will sink. It will not the source. It will sink, that means current will come from the load side. That is IOL by IIL. Okay. So if you look at here, if this is an IOL at the output side, output current, low output current, we know here we have some current, we call it IC. Because this is my collector terminal, this is my base terminal, and this is my emitter terminal. And when it will be output low, can you remember? When the transistor will be at saturation level, right? When the transistor at saturation level, it means like this. When the transistor at saturation level, at that moment we see VCE is equals to 0.2 volt, right? At that time we got this output low. Okay. So we can say the current coming through here, this IC current at this node, some current will going through this part, some current is going through the bus, because this is a node, right? The entering current is equal to the leaving current. So at this node, IC current is entering. So here there is two parts. One part is going through this way, which is IOL, and some current will pass through this transistor. We can call it ICS. ICS. That means reverse saturation current. Okay. So here we can write down, if we apply KCL at this node. If we apply KCL at this node, Kirchhoff's current law at this node, we can write down IC is equals to IOL plus ICS. Entering current is equals to leaving current, right? So what is my IC here? Can you calculate the IC? We can calculate the IC here, starting from here, VCC, through here, and reach here. So we can write down this IC is equals to I equals to V over R. Yes, sir.
The direction of this way is the IOL?
Yeah. IOL. Output current. So this is my output, right? This is my first DTL circuit, and this is my output we are taking. So output current is this way. As this is a low current, that means they are will sink actually. That's why this current is coming through here. So this is the IIL input. So I can calculate this IC equals to I equals to V over R by applying the Ohm's law. So what is the voltage here? VCC equals to -5 volt minus 0.2 volt 5 volt minus 0.2 volt divided by 2 kilo ohm. So you have to start from here, go through this resistance, coming through this saturation, coming through the ground. So this is the total circuit. You have to complete the circuit starting from VCC to the ground. So 5 volt minus 0.2 volt, because here it is in saturation level. At that moment, here the voltage drop across VCE is equals to 0.2. So here 0.2. So 5 minus 0.2 divided by 2 kilo ohm. 2 kilo ohm. So this is my IC current. So it is equals to 2.4 milliampere. What about this ICS current? This ICS current we can write down as ICS is equals to IB times beta. So beta is given 20, but we don't know the value of IB now. So we have to find out the IB value. So what is my IB current? This is my IB current, this is my base. So this is my base, this is my emitter, this is my collector, that's why it's called IC current. So what is the IB current? Here again we can see some current is coming through here and we will found some node here. Some of the current will pass through here, some of the current will go through here. If I name it this current as I, and this current is IB, and this current as I1, so we can write down here at this node. So again, we have another KCL. So if I apply KCL here, again apply KCL, we can see I equals to IB plus I1. So we have two nodes. At this node, I equals to IB plus I1. At this node, IC equals to IOL plus ICS. So you already got this IC current. Now we are trying to find out this IB current. Okay. So what is IB current? Now we are interested about the IB current. So we can write down IB current is equals to I minus I1. Which one is I? This is my I, right? So we are getting this current from where? Through this part. Through this part. So we can apply KVL here again. So I equals to, we can write down this I equals to what? Starting from here, VCC, then we have a resistance here. To reach here, how much? We have, if I'm not wrong, 2.1. Yeah. So it is coming through here. So when this transistor is turned on, when this transistor is turned on, we call it, this is a saturation, right? So that means whenever, that means you have a reverse bias here. That means we have some logic high. Logic high. When it becomes logic high, it becomes reverse bias. At that time, the current will not pass through here. That's why the current is passing through this way. And they will turn on this transistor. When this transistor is turned on, here already you have the forward bias. Now it is both, this is the forward bias. Both the side is bias is forward bias. We call it transistor is at saturation. So that means we are starting from here, going through here, go through here, reach here. So that means we have to apply 5 volt. Then what is the turn on voltage for beta? 0.7 volt. As I mentioned, we just consider that this is a silicon diode, this is a silicon based transistor. So 0.7, 0.7, 0.7. If you just think that it is 0.6, so 0.6, 0.6, 0.6. Okay? So we consider this is a silicon based diode and the turn on voltage is 0.7. So we can write down 5 volt minus 0.7 plus 0.7, sorry, 0.7 plus 0.7 plus 0.7, 2.1 divided by resistance 5 kilo ohm. So it will give you 0.58 milliampere. Here. So I'm going through. Okay. What is my I1 current? I1 current is just through this one. So I forgot to give you the resistance value. This is also 5 kilo ohm resistance. So here, look at this resistance. This resistance is just parallel to this one. VBE, base to emitter. So base to emitter is always 0.7 volt. this resistance. So this node or this potential difference is equals to this potential difference. They are in parallel. So when they are in parallel, they have the same voltage, right? So it is 0.7. You can write down I equals to V over R 0.7 divided by 5 kilo ohm. It is give you 0.12 milliampere. So now we will get our IB current. IB equals to I minus I1. So I equals to 0.58, I1 equals to 1.2. So it will give you IB equals to 0.44 milliampere current. Okay? 0.44 milliampere current. Now we will look for this IOL current. What is this IOL current? This IOL is equals to what? IOL will be IC minus ICS. IC minus ICS. So IC how much? We got IC. We got IC 2.4 milliampere. 2.4 milliampere. And ICS, now we need to find out, right? So beta value is how much? 20. And we get IB value 0.44 milliampere. 0.44 milliampere. It will give you 0.88, I think. 8.8 milliampere, right? So now we put this value here. Okay. So IOL is how much? Sorry, this is the IOL is equals to ICS. ICS minus IS. So now it is 8.8 milliampere minus 2.4 milliampere, right? 2.4 milliampere. So IOL is equals to finally it is 7.8 milliampere. Or we can just think this is 8. Sorry, what I'm writing. I'm sorry. I'm really sorry. IOL. So IOL is equals to what? 6.4. 6.4 milliampere. So we are trying to get the fan out. So what is fan out? Fan out IOL over IIL, right? Output load by input load. We already get our output load. What is my input load? So input is my this current. This current. So how much this current is? So you have to start from here. Look at here. We will go through here. It will sink to this transistor and it will reach to the ground. So you can draw this one. For getting this IIL, we have to start from here, VCC. It will go through this way. It will sink to the transistor to the ground. Right? To start from here, sinking here, go through to the ground. So IIL, input low. So VCC is same 5 volt. VCC is equals to 5 volt. I equals to V over R 5 minus diode drop. To drop across the diode is how much? 0.7 volt. Then it comes here. This is in saturation. How much voltage here? 0.2 minus 0.2. How much resistance they have to pass? 5 kilo ohm. So IIL is equals to 0.82 milliampere. So you get IIL, we got IOL. So IOL is equals to 6.4 and here it is 0.82.
How it is 0.2?
Sorry?
5 minus 0.7
Okay,
minus
so here, started from here, so 5 volt, then voltage drop across digital is 0.7.
0.7.
Then come here, so this is a transistor. Transistor at this moment, what is the transistor at this moment? Saturation. So VC equals to what?
Also,
0.2, so 0.2, then ground. So 5 minus 0.7 minus 0.2 is
so when I equal to 5 minus 2.1 divided by 5k, so that's we are taking 3 of diode,
1,
2,
2,
3,
3 this one.
and during the time it was not in saturation, so we
All
took
every time is saturation. Oh no, at that time we are moving this way. Oh. At that time, this diode, then second diode, then what? The transistor, right? The transistor is what? How much? VBE. Base emitter junction.
base emitter junction. That's
We are not going outside. We are going to the inside,
Yes.
input side. This is my input side. When you come to the output side, then we'll take the VCE. Okay? Got it, everyone? This is a good question. He said that why we choose 2.1? Because here 0.7, 0.7, 1.4. What the next 0.7? 0.7 because we are going through this side. So in the input side we have base emitter junction, right, of the transistor, right? The transistor is nothing but a 2 back-to-back diode. What is a transistor? It's a common emitter transistor. Common emitter transistor is nothing but 2 back-to-back, and this is an NPN transistor. So NPN transistor means like this. So this is my input side. So you have to turn on. So this is called VBE. This is my base, this is my emitter. So this is 0.7 again. And this is my output side. This is collector side and this is emitter side. When they will saturate it, we say that VC is equals to 0.2. So this is when we come from outside. This is my input side, this is my output side. Okay?
I have one more question.
Yeah, sure.
I get the IC is going down and there's
Which one? This
KCL.
one?
The IC.
Okay.
There's 2 KCL, I get it.
So here, okay, 1 KCL, yes. This is 1.
So
Come here.
VCC 5 volt, it's going and making the current go this way and down, and another point is KCL, it's making. How come the output from that VCC 5 volt is going through that place, and how does it affect?
Okay. So we have 2 things here. One is our this detail angle. This detail angle. So that means you can think like that. This is NAND gate, right? Inside this box we have this part. Okay. Now we are connecting another detail NAND gate. This is the fan out. How many NAND gate you can connect? So this portion is for that part, this part. So we have the same VCC because inside the IC we have only one VCC. It's not like that we have different kind of VCC. So we have the 5 volt. So we have the VCC here. This is the same line, power supply line. So this is come as I mentioned when output low, when we have the logic input high here, the AND gate will be get output low. So when the output low, that means output current is also low. Output current low means in that case, that means it is actually sinking. The current is sinking now. Current is not a sourcing. That's why current is coming back.
The current here is low and it's delivering.
It's actually sinking from the load.
Oh, got it.
Again, in the data sheet, it will mention how much current it can absorb. You cannot, so that means, for example, it can, maybe they mention it can absorb 40 milliampere current. That way, and if you have the input low current is 1 milliampere current, that means we can connect 40 NAND gate here.
Got it.
Okay. So if is IOL is 40 milliampere, is they mention in the data sheet, and IRL is 1 milliampere each, that means we can connect 40
NAND gates.
Next.
Wow.
So this is fine. So we get the fan out around, if I'm not wrong, around 7.8, which you can say almost 8. We can connect such 8 NAND gate here.
I have another question. So
Sure, no,
7.8, but we cannot put.
So it's maths.
It's a mass. So shouldn't we?
Of course, they should be properly described properly everything.
Yeah.
Just for a math, so we know more than 7.8, we can just choose 8.
That's what that's why I was asking. It's 7.8. If it's 7.8, we cannot put 0.8. So we shouldn't we counting
No,
like
no,
7?
it is number. It is the number. 7.8 means number.
Number.
So number of NAND gates. So you cannot put 7, 8 and 0.8 NAND gate, right? Either you have to add 7 and NAND gate or 8 NAND gate. So I think that, so if you calculate everything, if you choose all the values properly, it will give you the exact value, either 7 or 8.
Oh.
This is number. That's it cannot be a fraction, right? It's a number of gate. 1, 2, 3, 4. How many gate you want to connect?
So that's what I was asking. If this is number 7.8, so we can say we can go 8.
So if it is permissible, so for example, again we have to calculate this ampere, milliampere. Okay. So if for example, if it is 10 milliampere, for example, it can count 10 milliampere or for example 8 milliampere and it is 1 milliampere, of course you can go until 8. But if it is 7 milliampere, of course you cannot go 8. We should stick on 7.
But if that is not given, can we
It will
calculate?
be given.
Okay.
It is always given. In the data sheet, this is something that, for example, the BW20, it will be given. Because this is from the manufacturer. From the manufacturer, how they design, what is the, because when they design the transistor, there is some NPN transistor, there are how many magnetic areas are there, highly doped or not doped. So everything is defined in the manufacturer. So, for example, when you buy a resistor, they define, right, how much the resistor does and how much heat will generate. So they already have the calculation, they will give you. So in the spreadsheet that will be given. So this is how we can calculate the fan out, and in Excel we have to calculate like this same way.
2 KCL and the last one is the output.
Yeah. Okay.
This is the this is AND gate.
Detailed NAND gate.
NAND gate. Okay. We can calculate also the OR gate, right?
Yeah. And in last class we calculate RTL, right? Fan out for RTL. This is fan out for DTL. Okay.
Yeah.
Now we'll move to our next topics, the TTL, the most important, because this DTL circuit and RTL circuit is absolute. We don't use anymore the DTL and RTL circuit, but this is the basic, this is the starting point. Nowadays, we use either TTL or CMOS logic. So the CMOS we'll talk about after the spring break, that will be for the final exam. So we'll complete the TTL today, okay? So TTL stands for transistor logic. So here, of course, there are some drawbacks, like the noise margin, the power consumption, because still don't have the resistance. So we have to overcome those things. And of course, the space, whenever you have the DTL and TTL, it takes more space in the integrated circuit. The transistor will take less space in the circuit. That's why we more focused on TTL.
So TTL will take less space?
Yeah. If you want to increase the resistance value, it will take the more area.
In the
R is
TTL?
to go L by A.
In the TTL?
No. In the IC. We're talking about the IC. So if I talk about this TTL, transistor logic now, transistor logic, TTL. So they have the standard TTL. At first, I will start with the standard TTL, then we move forward the different kind of TTL. I hope I can finish. So there are 4 different kind of TTL, and TTL actually also have very high speed. It can offer 10 times speed than RTL and DTL. Okay. In the TTL circuit, it has 3 sections. It has how many sections? 3 sections. The first section is known as, in some preference, they name it an input section, and someone mentioned as this is a current steering section. Okay, current steering section of the input section. So let me draw the circuit first, then I will describe how it works. Right? And this is a NAND gate, except this one will get all one, right? All one. This is opposite of AND gate. And here we'll get 0. So this is the NAND gate. So we need to see whether my circuit will perform this truth table or not. Okay, so these are the input A, B, and C. A, B, and C. Okay, let's see. So when any input is 0 or all input are 0, when any input is 0, either A is 0 or B is 0 or C is 0, we can see when any input is 0, output should be 1. Or when all input are 0, output should be 1. So okay, so if I think that if any input is 0, so here if I just draw this transistor part separately here, for our understanding, if I draw our transistor part separately here, what you can see, this is the base. As I mentioned, the transistor is nothing but 2 back-to-back diode, right? It's a 2 back-to-back diode. So that means this one, right? This is N, P, M transistor, because arrow is from P to N. So NPN transistor, right? This is arrow is from positive to negative. So this is N, this is P, this is N. Okay. So P-N, P, P-N. So this is my base emitter, this is my base emitter junction, and this is my base collector junction, this is my base collector junction. Okay? Am I going fast or okay? Everything fine? So I just draw this transistor here. We already know the transistor is nothing but 2 back-to-back diode. So we have base emitter diode, we have base collector diode. Base emitter diode, base collector diode. This is my input side, this is my output side. We already know that. So as I mentioned, whenever we give input to any input is 0. That means logic 0. The logic 0 in the TTL circuit we just apply 0.2 volt to 0.8 volt, right? If I'm not wrong, yeah, 0.2 to 0.8 we consider the logic 0 in TTL circuit. So that means you give 0.2 volt here. And here the VCC is here. So from this resistance we have the VCC here. So this means it is in forward bias because negative or low potential is connected to the negative side, high potential connected to the positive side. So this diode is in forward bias. If the diode is in forward bias, the current will flow as this is a VCC. If I take another color, current will flow this way, right? Current will flow this way. So as I mentioned, this some reference books they mention this section is known as input section, and some reference book they use as a current steering. They will control the current flow. Whether current flow this way or the current flow will this way. Okay. Why the current will not flow this way? Here, so it requires only 0.7 volt here to get this up. But here, if you come here, it needs to turn on here, then it will go through here, it needs to turn on this one. So 0.7 plus 0.7, 1.4 volt. So that means it has some higher potential. So current will always flow in the lower potential area. So current will flow this way. So when this current flows this way, that means this is in forward bias, this diode in reverse bias. This diode is in reverse bias. If this diode is in reverse bias, that means we don't have sufficient voltage here. Maybe we'll have, so for example, if it is in reverse bias, maybe we'll have around 9 volt here. But to turn on this diode here and here, it requires 1.4, minimum 1.4. So this transistor will remain off. If this transistor remains off, actually it will be 0.2, very minimum voltage here at this point. So it cannot turn on, because to turn on it requires minimum 0.7 or 0.6 volt. So this transistor will remain off. If the transistor remain off at this voltage, this is 0 or some voltage here, it will not enough voltage to turn on this transistor as well. So this transistor will also remain off. If this transistor remain off, that means the current will flow through here to here. This is open circuit. Off means this is an open. We can just remove this one. So current will pass through here. So output voltage is V1 minus VCC, some IC, RC. It will be around 3.6 volt or something volt. So you already know for TTL logic circuit, so logic 1 should be in range of 2 to 5 volt. So we can just consider it to be 3.6 volt. So we'll get what? High. For any logic 0 input, our output will be high.
Can you explain this one again?
Which one? This one?
The.
So whenever we don't have sufficient energy here, it cannot turn on this transistor. If this transistor is not turned on, that means this is an open. That means current will not come through here. If the current don't come through here, we will not have sufficient energy here to turn on this transistor. So if this transistor is turned on, that means this is also open. So we'll get output from where? We'll get output through here, VCC. So VCC minus ICRC, because this is the voltage drop. So we'll get high output voltage. High output voltage means logic 1. Okay? Now, when all the input is high, means now we give, for example, 3.6 volt, 3.6 volt, 3.6 volt. That means logic 1. Okay? Whenever we give this logic 1, that means this is a now higher potential than this potential. That means this diode becomes reverse bias. When this bias reverse bias, now the current will flow through this direction. So that's why they are also known as steering, current steering section. Now it will decide the current will flow here. When the current flow here, that means it has to have now sufficient voltage here to turn on this transistor. When this transistor will turn on, that means it will give some output voltage. It will have sufficient energy to turn on this transistor. So now the transistor will turn on. Now it will have some short path. So output will be from here to with respect to ground. So when the transistor is in forward bias, because we have the sufficient energy, and this portion is already forward by this biasing voltage, so both are forward bias, so the transistor is in saturation. So we know when the transistor is at saturation, we have 0.2 volt, and when it is 0.2, it is correspond to logic 0.
I have one question.
Yes.
When A is 0, that's 0.2, we know the current is flowing this way because of the forward direction. Why the current is also flowing that way?
When any input is 0, current is not flowing in this direction. That's the thing.
Okay.
When the input, so for example, you
but
can see
high voltage is going over there.
So it depends on current, right? So if it is a short path, if it is low resistance and it is a high resistance, current will flow which one? In the
low resistance.
So if there is no current, there is no voltage drop. If there is no voltage drop, it will not turn on this transistor. If there is no transistor, look at here, there is a resistance, so there is no current. So if there is no current, there is no voltage drop. So this is 0. So if it is 0, that means it is 0. To turn on this transistor, we need 0.7 volt. But here no current. So as there is no current, there is no voltage drop. So it's a 0. So this is off. So if this off means it is separated from the circuit. Okay?
Then the voltage will go
through
that
this one, and we get the output high. But there is a problem with this circuit. Here we have the current passing through this RC3, right? The biasing resistor of the third transistor, RC3. When it is, let me see what statement to make sure, yeah. Okay. So if we want to, whenever we give some output load, so we have to get the connection to something else, right? In the output side. So if I remove these things now, if I just draw the output side, in the output side we have what? This one, right? This is the output side. So whenever we connect some load here, that means some other transistor or something else, so that means it will have some load capacitance here. Some load capacitance is here. And this was my T3, transistor 3, right? This was T1, in the middle we have T2, this is the T3, right? And here, either it will be turned on or it will be turned off. Okay. So when it is turned on, that means current is flowing through this way, right? So a huge current can pass through here. So to restrict that current amount, we have to choose this R3 value very high. And at this time also the capacitor will discharge. When this T3 is off, the current pass through output side. At that time, this R3 value should be low. That means this resistor is known, that is the name of this resistor, this is known as pull-up resistor. Sorry, passive pull-up resistor, yeah. Passive pull-up resistor. So that means this resistor need to vary between high to low, When the transistor T3 is on, this R3 value should be very high, so that it can restrict some current, otherwise it can damage. When T3 is off, that means we want to get the current output side, then R3 value should be low. Otherwise, if the voltage drop is here very high, then we will get some voltage output which will be lower than the noise margin. Because we know, we already detect that this is for the TTL, maybe for 2 volt to 5 volt, we consider logic 1. So at least 2 volts should be necessary here. So if we have the higher voltage drop here, maybe here we will get 1.9, 1.8. So it cannot detect logic high. So that's why we need to have lower resistance here. But on the other hand, when T3 is on, when it is logic 0, but most of the current passes through here, to protect it, we need some resistance high value. So we need some variable resistance here. So to overcome this one, instead of this resistor, we should connect another device. This is known as totem pole. Totem pole, that means we have to connect two transistors, one after another. This condition is known as totem pole. So in the input side, we still have the same thing. Here. So if I just draw here the totem pole resistance, again we have this transistor T2. We have this resistance R2. We give this input tree here. So this is T2, this is my T1, sorry. This is T2, this is T3. So far we have this one, right? Previously we have a resistance here. Can you remember? Previously we have a resistance here. Now instead of this resistance, we will replace this resistance with a diode and a transistor. This is T4 and this is diode, and we still take the output here. This structure, this portion, this section is, as I mentioned, this section is known as input section or current steering section. This middle section is known as phase shifter, okay? And this third section is known as output section, In some reference book, they also named it as totem pole section. The totem pole means you connect one transistor after another. So this is for totem pole structure. So here it is T2, so it is R2, it is T4, so we can say this is R4 now, and this is RE2. The operation is almost same. Now we just see how it will work, okay? So this is called TTL, totem pole output. TTL, totem pole. TTL, totem pole. TTL, totem pole. Okay. So again, this side is same. This section is same, right? So still we are talking about the NAND gate. So when we start again with 0.2, logic 0, 0.2 volt. That means my base emitter junction is in forward bias. My base collector junction is in reverse bias. As this is a reverse bias, it will not have sufficient energy to turn on this transistor T2. So T2 is off. When T2 is off, T3 is also off. Okay? So what will happen about the T4 now? Okay. When T4 is off, T2 is off, that means this T2 is off. This T2 is off means we have disconnected this portion. We have disconnected this portion, right? You can say. Now to turn on this T4, we have to have the current or voltage on here. This point. So at this node, how much voltage we require? We require 0.7 volt. We require 0.7 volt. So we have VCC equals to 4 volt or 5 volt here. So it will be a sufficient energy at this point to turn this T4. So the T4 will be turned on, and we will get our output through this way.
Why not it will turn that one on? T2 and T3?
Because here this transistor is already off, cut off. Because to turn on the transistor, we need at this point how much? 0.7.
0.7.
Your base is connected to here, but this one base is connected to here. To turn on the transistor, you have to give what? The current to the base. Your base is here. This is my base of T2. Here we don't have sufficient energy here to turn on here. But the base of this T4 is connected through R2 to the VCC. So it has sufficient energy. But it is not only T4, it is also have B. So to turn on this one, then we have to reach here, right? Then we have to reach here. So 1.4, 1.4. Plus we can say, as this is off, how much is the V out? How much is the V out? When we are turned off? 0.2. Because this is logic 0. Because we divide the logic 0. Sorry, not V out. Sorry, we'll get this. Sorry. So we'll get output from here. We'll go through here to here. So it will be turned on. So we can write down T4 will turn on by RC2, and then it will get output for RC4, T4, and diode. Okay? So when it will be turned on, we'll get our output through this one. So basically, it depends on either it will be turned on or turned off. We need to check the condition, whether my transistor is in on or off. on and off. So again another thing, okay. So when all the inputs are now high, logic high, so I will go to the next condition, logic high. That means you give some 3.6 volt, 3.8 or 4. Then this base emitter junction will become reverse bias, right? Reverse bias because you give the high potential to the negative terminal. So it is a reverse bias now, right? So if this is reverse bias, then it will become forward bias, or it will have sufficient energy to go through here. And this transistor will now turn on. When this transistor will turn on, it will turn on this resistance. When this transistor will turn on, we will get the output from here to respect to ground. At this moment, it is VCE is equals to 0.2, we will get 0.2 volt here. Now, what is the condition of T4 now at this moment? Okay, so at this moment, what is happening? So to turn on the T4 depends on this voltage, right? Depends on this voltage. So what is the voltage here? At this voltage, to turn on this one, we need how much? 0.7 plus 0.7. 1.4 volt is necessary, right? Look at here, this is important. Now, this one is already turned on. When it is turned on, when you give the logic 1. When you give this logic 1, this portion will become reverse bias, this portion will become forward bias. Current through this way, T2 turn on, that's why T3 also turn on. When T3 turn on, we get our logic low. So we already get it, this one, fine. But what is the condition of T4? To turn on the T4 or to turn on the T4 depends on what? The voltage drop across the base here. To turn on this T4, we need at least 0.7 plus 0.7 and also 0.2. Right? So 1.6 volt. But how much voltage we have here now? How much voltage we have here now? Anyone? We have, at this point, we have only 0.9. How? At this point, we have only 0.9. Because we have 0.2 at VCE to saturation, VCE to 0.2 and 0.7 for VBE3. So many drawing is here. Let me remove some, then it will be easy. Now I am telling what is the condition of T4. To turn on the T4, how much voltage you require? 1.4. Because to turn on this one, you have to reach to the ground, right? Then it will turn on. You have to complete the circuit. You have to start from here, go through here, 0.7 volt drop here, come here, 0.7 volt drop here, then you will go to here, then you will go to the ground. So if you take the consideration of the output voltage, it requires 0.7 plus 0.7 plus 0.2, 1.6. So at least 1.6 voltage is required to turn on this transistor. But I mentioned we have here at least only 0.9. How? Because now my transistor T2 is turned on, right? So when it is turned on, that means you can see it is turned on, 0.2. Then it will go here, and it will see this is also turned on. This turn on means VBE is equals to 0.7. So from here to here, if you think about the parallel voltage drop, from here to here and here to here, they are parallel. So it is required only 0.2 and 0.7. Here we have only 0.9. So it will not have sufficient energy to turn on this T4. So when the T4 is not turned on, what will happen? T4 is not turned on means this is cut it. So as I mentioned previously, we saw that when the transistor T3 was turned on, high amount of current can pass and damage this transistor. Now we can restrict this current. We can restrict this current. And whenever it is turned off, to get the logic high, it is already have only 0.7 and 0.7, 1.4 volt is dropped. So if you just minus 5 volt, minus 1.4 volt, it will get 3.6 volt. Okay? Because here we have given the VCC 5 volt. At that time we have a drop of 0.7 and drop of 0.7. 5 minus 1.4, it is 3.6. So get the logic high. No issue. No, we don't, depending on the resistance value, now we don't need to change the value of resistance here anymore. And when it is turned on, then we are thinking that maybe high current can pass through here. Now the transistor T4 will be turned off, so it will not allow any high current here. So this is called the totem pole circuit. Okay. So don't worry, I will have upload this hand notes. So I have written everything here. You can see here. So can I, if I draw the totem pole NOR gate, this is NAND gate, right? So I draw the NOR gate. TTL, totem pole, NOR gate. TTL totem pole NOR gate circuit is a little bit complicated. Let me draw this one. So this is input A, this is input B. So here we cannot use multi-emitter transistor. For each input we have to have separate transistor. So this is given input A, this is given input B. Okay? So then we need to take the same thing. From here we have to take the output here. Here also we have to take the output. Then these two will be given connected in parallel. And this is the rest R4. Then we will keep the final transistor here. So here we will have our diode. Then we will have our transistor here. That is input to the here. Then we have this resistance here. So this is a little bit complicated one, but we can amplify. So if in our previous stage, in the previous design, when we designed that TTL NAND gate, totem pole NAND gate, we just think that we have one input here, right? Look at here, we just have this input, multi-emitter input, then we take the output from the collector, give it to the next transistor, right? Next, from this next transistor, we give it to the output to the final transistor. Now here we have to use two separate transistors for two different inputs. So that means A and B. So here it is going to here, same input is going to here. So A input is going to here, B input is going to here. Then they connected in parallel. Finally, they get it to the final output. Okay. So this is the totem pole. So we can write down this is T1, this is T2, this is RB2, this is RB1, this is T3, then it will be T4, this will be T5, this will be T6. This is RE4, this is RC6, this will be RC4, that's it. So this is B, my BCC. Then it will work something like that. Similarly, so you just think the same way. Now, just instead of one transistor, now you have 2 transistors. That's it. Okay, so you can think, we draw this one like this. We have now 2 transistors, so we can think like this one. And we can calculate this one. Okay, so I have written these things. You can go through here. You can easily find out. I hope, don't worry. So every time you just need to check whether the transistor will be turned on or off. Okay, so as this is an NPN transistor, still both are NPN transistor. So that means if you give the logic 0, it will be forward bias. If you give the logic high, it will be reverse bias. So if this is a logic 0, if it is a forward bias, current will pass through this way. If it is a logic high, it will become reverse bias, current will go that way. That's it. Okay. So for example, just I will give only one example. When it is 0, 0. So that means both input is 0. A also 0, B is also 0. That means both are in forward bias. In both cases, current goes through this way. If the both cases current goes through this way, then this transistor and this transistor will be what? Off. If this transistor will be off, this transistor will be off. If this transistor is off, current will take output through this way. NOR gate is when 0, 0, it will give you 1, right? NOR means 0 plus 0 equals to 0, or NOR means 1. So we get 1. And other than that, every time we will get 0. So if you just take one example, if A is 1, logical 1, and B is logical 0. So what will happen? So when any input is low, so if you look at here, A is 0 or B is 1. So in that case, what will happen? As this one is high, so this transistor become reverse bias, right? This one is reverse bias, but this is forward bias. So if it is forward bias, it will be off. But as this is a reverse bias, it will be on. Okay? So when T4 is on, T3 is on, then what will happen? So T6 will be off. So if T6 is off, then we will take the output high. So when that is on, so as this is on, it will turn on this T5. So when it will be T5 is on, then we will get output BC equals to 0.2. Okay? The next circuit is known as TTL open collector NAND gate. Open collector. This is very simple one. They just mentioned that if you have a TTL, which one is collector? This is my collector terminal, right? We take output from where? Collector terminal. Look at here. Every time we are taking output from, this is base, this is emitter, this is collector, right? We are taking output from where? Collector terminal. At the very first circuit, we talk about the standard one, right? At that time, we have a resistance here. Can you remember? A resistance here. We just replace this resistance with this total pole circuit, right? Now, if I remove this one, neither a resistance, neither a total pole. This is known as open collector. That means your collector is open. That means inside your IC, the collector end is open. For example, the pin number 7 or pin number 8. Then you have to connect a resistor externally to that pin. Inside your IC, this is called open collector, TTL. That means inside your IC, the design is something like that. That collector terminal is not connected to anything. So whenever you have IC, and for example, they mention this is pin number 7. At pin number 7, you just connect the resistor. Then you just externally connect this resistor to the open collector. This is known as TTL open collector NAND gate. The operation will be the same because everything is rest of the thing is same. Okay, rest of the thing is same. You just need to mention that whenever it is on, we already get VC equals to 0.2, that logic 0. But whenever we need to find out the logic high, we should have some connection from VCC to RC to get the logic high. Otherwise, it is always logic 0, 0.2. Okay? To pull up, we just need a external resistance to the VCC. The final one. This is known as TTL tri-state logic circuit. TTL tri-state logic. So it had, from the name we can understand that it has 3 states, right? It has 3 states. The first state can be a logic high, of course, we know. It can be a logic high output. The second state is logic low. And the third state is the new one. It's called high impedance state. So how the circuit will look like? If I draw the circuit here, still the same, only one connection will be new. So let me draw this one. So this is a common base. This is RB1. Then we give it to the second transistor base. That we take here, RC2, then we give it to the third transistor. Sorry. Then we have this totem pole. Everything is same so far, okay? VCC, RB1, this is T2, this is T1, this is T3, this is T4. Everything is same, okay? So, you can say RC4, RC2, RE2. Everything is same. Only one thing we have in this circuit, they call it an enable input. That is the second input to the multimeter. This is known as enable input. Multimeter transistor, we just give one input here, A, and we add another input as an enable input. And this same enable input will be given through another diode to the collector here. So this is the new connection only. And another input is given through a diode to the collector. Okay? So this is called another input. So let's see with the input when A equals to 0. That means my enable input is 0. So if you look at here, so if E equals to 0, that means it is connected to the load potential to the negative terminal of the diode. and positive terminal is connected to VCC. So this is in forward bias, this direct become forward bias, because E is 0, that means 0 potential, 0 voltage, or low potential connected to the negative terminal, and high potential connected to the positive terminal. So it is become forward bias. So when it is become forward bias here, we can see. So when it will be happen, whatever the T1, whatever the input, it will not depend on that input, it will turn on this T2. Imagine that whenever E equals to 0, no matter what is the input A, the T2 will turn on. T2 will be turned off. Okay? So when T2 will be turned off, we already know T3 will be turned off. But in so far, we saw that whenever this T3 was off, my T4 was on. Can you remember? When the T3 was off, my T4 was on. Because when T4 was off, through this one it was off. Now, what will happen? At base of B4 required how much? As I mentioned again this time, how much voltage we require? 0.7, 0.7, 1.4. To turn on this T4, we need at least how much? 1.4 volt. Because if you have to on VBE 0.7, then this VBE 0.7, 1.4. So, but how much voltage we have here? We have only 0.7 voltage. Here we have only 0.7 volt because it is only 0.7 volt here. Right? How much voltage we have here? Only 0.7. This is the same voltage up here, right? Because this is connection here, we get this connection to here. This is the only special connection. We give enable input here to the connector terminal of this two T2. Okay? So here we have only 0.7 volt. So whenever it is a 0.7 volt, it will not turn on this transistor T4. So that means at that time, both T3 and T4 is off. It will be a very high impedance. High impedance. Now when E equals to 1, this diode will become reverse bias. Now the normal operation will work like an inverter. So when A equals to logic 0, we will get logic high. When A equals to logic low or high, we will get. So if A equals to 0, we will get the output equals to high. When A equals to 1, we will get output equals to 0. Okay? So, as I mentioned, logic high, logic low, high input impedance. Here we have just one extra input, this is known as enable input. In some cases this kind of circuit necessary, so that's why it is known as tri-step logic. So if you want to use your TTL as a high input impedance, you can have this enable input. That means it is simply it is a NOT gate, TTL NOT gate. It's an inverter circuit. So in the TTL NOT gate, we have only one input, right? NOT gate is like this. What? If you give 0, it will give 1. If you give 1, it will give you 0. So this is the TTL NOT gate. But in the TTL NOT gate, you just add one enable input. It will act like a high impedance. So this is all about the TTL. And I will upload these notes. Have a nice break. Enjoy your break, but also please try to study these things. After the break, we will continue the CMOS circuit first week. But if you have any question regarding these things, please feel free to ask me.
Were you thinking the test being a week right after spring break? Or?
Right, after the, so from here, 2 weeks from here.
I have another question. So do we need to, I get it, we need to draw the diagram and explain how high and low in internet.
So usually I will also upload the sample questions so that how you can practice. Sometimes I will ask you to draw the circuit.
It's fine, we
Sometimes
can
I will
draw
ask you
it.
to calculate the fan out. Okay.
Those fan out is okay, but here we don't need to
Here
calculate.
you don't need to calculate. You just need to draw the circuit.
This circuit is